Vishnu, good evening.
Hi, Ash. Good evening.
Thank you
You
again.
can
Yeah, I can see
you can
you.
hear me? Okay.
Yeah,
All
see
right.
you and hear you loud and clear.
Cool.
And thank you again for doing what you're doing. This chapter is one of the most exciting, as Chip notes in the
Yeah.
conclusion. This is the one that everybody was looking forward to, and it's very well written, and it has
Mm,
potential for just expanding to so much more.
yeah, exactly.
Let me.
Tried my best to create the slides and presentation, so I'll give my best. Yeah, let's see.
Uh, we need to sharing. Let me see if I can find. Can you share, Vishnu?
Yeah, just a second.
Okay.
I think I cannot share my screen. I
Yeah,
think Ash will need to turn on.
I'm having the same problem too.
Okay.
Does anyone have a Zoom account access that they can, or a Zoom account that they control that we can all jump on, where you have the rights to enable sharing? Mayank, any chance you might have the Twimmel Zoom?
Let me see.
Okay, we're using Santiago's private Zoom, and it is not letting us share. And I've messaged him.
Okay, he told he's traveling, right, today?
Yeah. So gang, everyone who's joined, just bear with us for a short bit of time until we can get a Zoom link set up so we can share. Modern day problems, you know? If we have to use this one, Vishnu, you have your content in as slides that you can send the link and you can just go from slide to slide and tell everybody here, I'm on page this or page that. Go ahead, Patrick. You're on mute. Patrick, you're on mute. Patrick, you're still on mute. Let's see if
Okay, there. The way I did it was if you bring your cursor down to the bottom, thing sort of pops up and it says share screen.
Yeah,
Yes.
now I think I can share. Yeah.
Oh, there you go. Yep, now we can share. We are good to go.
Yeah.
All right. Let me share one thing and help us just to get started. I'm only going to take really no more than 30 seconds here. So for everybody who's joining, thank you so much for making time. Let me also begin. For those who celebrate and for everybody, I want to wish you a very warm Eid Mubarak. And so thank you again. We're on, so as we do the AI engineering with Chip Huyen's book, really quickly, we meet at this time every Sunday. We aim to get through a chapter every week, and everyone's supposed to have read the chapter before coming to these sessions so we can have a very productive session, which is led every week by a volunteer. Today, we have the amazing and wonderful and brave Vishnu, who will be walking us through this. And I'll come back to this slide at the very end. Today, we're going to cover RAG and agents, retrieval augmented generation and agents. And at the end of today's session, I encourage every one of you to really consider offering to be the leader for us for Chapter 7 fine tuning next week. And with that, without further ado, Vishnu, take it away.
All right. Okay, I think I got some other issues. I think I have to quit and reopen Zoom. So I'll be back in a second.
Sounds good.
Is Santiago not available or?
No, he is not, but he did message me back to say that he
Mhm.
enabled sharing, so we should all be able to share. As I was able to get on, Patrick was able to get on.
Yeah.
So here's Vishnu. Perfect, Vishnu, we can see it now.
All right. Okay, then let's start. So yeah, even I think this is one of the challenging chapter. A lot of interesting stuff happening inside this chapter because I think RAG was something that we all I think learned and heard a lot in LinkedIn everywhere last year, and I think this year is the year of agents. I guess so a lot of new and interesting stuff. So I believe uh, I've done some research and then put in a good slide for you all of you guys. So if there is anything, let me know. I mean, it's a discussion book club, so let's learn together. So with that said, let's start. So a small recap. So till the chapter 6, I think we learned a lot about the importance of context. So whenever we chat with a large language model, we write some of the instructions, and then along with the instruction, if the model really wants to know what it needs to generate, or it needs to create an output, then it needs a context. So all the models you might know, right? We have our models trained on 2023, and it won't be able to like answer the questions related to 25, and also we need context. Um, so dominating patterns for the context construction are first one is RAG, or retrieval augmented generation. That means the model can retrieve the information from some external data sources. And the second one is agents. That means the model can use something called as tools, what we're going to see in later. So tools like web search or some news APIs to gather the information. So these two are the main ways in which you can enrich the model with some kind of context. So that's what we are going to do in the next 60 minutes. So starting with RAG. So RAG, I mentioned it's retrieval augmented generation. But the thing is, it started with with a paper called Reading Wikipedia to Answer Open Domain Questions. Okay, so this is what it started with. So here you can see that the system just collects all the information or parses the information from a Wikipedia article, and then using that information, the correct answer was retrieved. So this is what it started. I mean, how it started. So then we come into the RAG. I mean, the proper retrieval augmented generation. So this particular name was coined by Lewis et al. In 2020. So here we see that we don't need to like give information, all the information for the model to generate the exact information. We just need to give the right amount of information. So that's the right amount of retrieval is needed for the model to generate the information. And we don't need to like dump in, I don't know, tens and thousands of tokens or information. We just need to give most relevant information for the model to extract the information to the user. Otherwise, what happens is that, yeah, if you give like a lot of information, a lot of unwanted context to the model, then obviously you will land in hallucinations. So this is how it started. The RAG pipeline is the introduction. I'll come back to the architecture in the later slides. So RAG, a little bit more about RAG. So it's.
So Vishay, am I missing something? I don't see any slides. Is it being shown somewhere else, or is it? I see Adeline something, some company website.
Okay.
So is the problem only I'm facing, or anyone else?
For me, I'm getting information that I'm sharing my screen. So if someone else can confirm.
Yeah. Is anyone else able to see the slides?
I'm also seeing the Adeline extract transform search website.
Yeah, same here.
Yeah. Sorry,
Okay.
can't see the slide.
Thanks for the message. I'll share it again.
Now we can see slides. Do you want to begin really quickly, do a recap from the?
Sure.
Sorry to interrupt. Please go ahead.
So now also you can see the slides, right? All right. I don't know what happened. Okay. Sorry for the trouble, guys. But then, okay. Well, then let me restart again. So what I was telling you, we said, okay, the RAG, the thing, it started with a paper called Reading Wikipedia to answer open domain questions, wherein the authors tried to give the exact information or exact exact context to the model, and then the necessary information was retrieved. So this was the first initial, I would say, the pathway to the complete RAG thing, and then the exact RAG name, or the retrieval augmented generation, was coined by the paper by Lewis et al. For the knowledge intensive NLP task. And then the solution was that the model doesn't need a lot of information. It just needs the exact context to give you the information that a user might need. And then if you bombard the model with a lot of extra information, then obviously you land in hallucinations. So this is just an introduction, and I think I'll go into the detailed architecture diagrams in the later slides. So what is RAG? So RAG is a technique to construct context specific to each query. So if you ask a query to the model, so RAG tries to create the exact context what that particular query needs, and then it helps the user to get to the answer. So for each of the queries that you might ask the large language model, the queries or the context might be different. So it's not working on the same context. So the context is specific to the queries. So then an interesting analogy, what I read from the book is that, so the context construction is for foundation models is similar to the feature engineering that we are familiar with the classic machine learning models. So in the classic machine learning models, if you want to, I don't know, forecast a temperature rise in a city, then what you give the model is all the exogenous variables like temperature, I don't know, humidity, etc., and you are not going to give in the population of that city. So that's the exact thing what's happening here. We are giving the specific context to the foundation model in terms of RAG. But then this actually stuck me, as I told you in the initial introduction. I mean, RAG, we have been hearing about RAG since 2020, and then most of the papers, I mean, we have seen a lot of different varieties of RAG, naive RAG, or the thing what we all call as basic RAG, wherein you just build some retrieval and then get the documents out of a knowledge base, and then you use a large language model to generate the response. So that's the basic RAG. So once everyone starts with that, and then I think people were, well, it was not easy to scale the quality, right? I mean, so when you have like multiple documents, then somewhere the quality of the RAG gets decreasing, and then people start yelling out, "Hey, RAG is dead." There is something better now. I don't know, contextual RAG, or maybe caching RAG. I don't know. There are like, I don't know. Last year there was like every week there was some new kind of RAG. But there is one thing I want to like ponder here. So is RAG really dead, or is it alive? So what I believe is that it's still alive. So I'm glad that even Chip in her book also written that. I mean, in her perspective, RAG is also it's alive, it's well and alive, and people are using it, and then it's far better than the other alternatives that comes in. So why I meant it is here to stay is because so here we can see that, I mean, as the years progressed in all these large language models, we have seen that the token length of models are increasing. It's even multiplying in, I don't know, 3 times, 100 times might be. And then people are telling, okay, I don't need a RAG. If I need to ask a question about a book, I can give that complete book to the large language model in the context, and then I'll try to get my answers out of that. So I think this is one of the famous, I would say, non-RAG advocates sentences, right? You don't need a RAG. I'll just pass the book completely to the large language model. But then what I've seen is that, so it's also an interesting paper. So here also we can see that, okay, as long as your the context length of the model increases, the model finds difficult to get the exact context for that particular user query. So that is one thing. So in between, the information will be got lost. Some models prefer the information on the top. Some models prefer information at the bottom of the context. And if you try to like give or pass in the complete book, the information will be lost, and then model will try to hallucinate. And then for that particular reason, right? So I'll say that, okay, I'll pass an exact book. So next year, maybe that book is bigger, and then the model context remains the same. So you cannot pass that same book. So I really believe that because of all these reasons, and I sense it to be valid too, RAG is here to stay. And then, yeah, I mean, I'll share the slide with you guys, and later you can go into this paper, and then taken the screenshot from that paper. So here it's clearly mentioned that as long as, I mean, even if you are increasing the token size of the models, the accuracy of the models is drastically reducing. And then another issue with the context is that, I mean, if you have like extra context, if you try to pass in extra information to the model, then of course you'll have to incur extra cost. It's not that cheap, and then there is a potential to add extra layer of latency also. The model needs to like parse through the complete book. So if you need just an answer out of a single page, the model need not go through the complete book and then get the answers for you, right? So that is the thing. So with this said, I still believe that RAG is here to stay. All right. So so now coming to the architectural part. So RAG, it has basically 2 stages. One is the indexing stage, wherein it gets the information from, and then second is the embedding stage. So the indexing stage is that, so you have the data sources, I don't know, some technical documentations, some user manuals. So some example from my practical life. So in my industry, so I'm working in Bosch Rexroth, so we use RAG to help our customers get the answers of some queries in a far easier way. So the customers, if they have some issue with, I don't know, some valves, some motors and pumps, they had to like go through all the technical manuals, and then they had to like get the answers for the problem. So what we built was a RAG pipeline, wherein we indexed all the technical manuals, all the troubleshooting documents, and then the user were able to get the reasons for a fault in a far efficient way. So taking that as an queue, so then my example for all these data sources will be my technical documentation and troubleshooting documents. And then we have to like enrich all these documents with some metadata, and then we chunk all those information. That means you divide a big document into smaller documents or chunks, enrich that with some text and metadata, and then you embed that using an embedding model. You convert those documents into numbers basically, and then you save that in a vector store. So that is the indexing stage. The later part is the querying stage. So now you have enriched all those technical documentations here. As an example, so in the querying stage, what happens is that, so when the user asks, hey, I have an issue with that, with a pump, for example, so the query is then also, the query also goes through the same embedding model, and then it searches the vector store. It gathers the relevant context from the vector store. So there is some algorithms what helps us to like query the embeddings. We'll discuss about that in the later slides. Once I get the relevant context, I combine the prompt with the relevant context and then pass to the LLM, and then I'll get the response. So that's the two stages of an RAG. As I said, first one is indexing, getting all the documents, saving that in vector store. Second one is like getting the information out of the vector store by getting the relevant context. All right. Do you guys have any questions here, or am I good to continue? All right.
One question.
Just one. Yeah, please go ahead.
Can we go back to the indexing stage?
Yeah.
So, what kind of metadata are we talking about here?
Yeah. So metadata is something like, I don't know, page numbers, for example. So if you're indexing a document, so you chunk the documents based on, there are a lot of algorithms like a lot of chunking algorithms like recursive algorithm or sentence-based algorithms or context-based algorithms. So based on the algorithm, you take, for example, if you take a paragraph-based algorithm, you chunk the paragraph out of a document. Before you embed that in the vector database, you take the page number, you take the heading, you take from the markdown, you take which heading that paragraph is based on, and then you take the book name, you take maybe the collection name, all those things. So all those things come in metadata. So the cool thing with metadata is that so when we basically know that, okay, I'm gonna so if the LLM knows that, okay, the user is querying something related to this set of books or this set of collections, I can use the metadata to land in the embeddings. I don't need to like query my complete data bank. So it's actually faster.
Okay, so how do we format this information like text and metadata? So how do we format that structure?
So when you, I mean, inside the vector data, inside each of the vector data banks, I mean, you have a possibility to like store the embeddings. So the text are stored as embeddings. You convert the text, whatever you read, you store that as an embeddings, and along with the embeddings, you can store this as an metadata. Metadata is basically a JSON or it's a dictionary if you want to go into technical stuff. So you save those things together.
Fine.
All right. And then the cool thing with metadata is that, I mean, I just want to ponder this, I mean, to stress this point. So what I have seen is that, I mean, if you're just using an embedding, then when the model needs a particular context, then it needs to like search the complete vector data bank. But then if you have have a metadata, then you can, using the metadata, you can confine your embeddings, and then you just need to like search in that particular area where your metadata is there. So if I know it's, I mean, the user is asking about this particular for example, in my case, pumps. So I can have a metadata called pumps, and then the model will only search the embeddings related to this particular metadata. So that's the cool thing about that. All right. So retrieval. So I think based on this explanation, last two slides, we can see that the large language model, it's actually just doing a generation, right? It's not doing doing a real work out there. And even I believe that, I mean, RAG pipeline will leave only if the retrieval you built are good. So if you have a bad retrieval algorithm, or if you have a bad retrieval in your RAG pipeline, then what the model will get is really bad. So when you give bad things to the model, you can accept only bad things as an output. So everything starts here in the retrieval. So that's what we are gonna see in the upcoming slides. So there are like two types of retrieval. So one is sparse retrieval. It's also known as term-based. So Chip used this term-based vocab for that. The other one is a dense retrieval or an embedding-based retrieval. So these are the two basic retrievals. I think in the previous chapter, I think we also have read that all these term-based is also known as lexical matching. So that means you just try to get the vocabulary. So if the user asks something about a pump, so my model will check for all the words that are match and try to match all the words pump. It doesn't know what context it is. It doesn't know the semantic meaning of those things. And then the next one is the dense retrieval. So again, as I mentioned, it's semantic. So if I ask about transformers, the lexical matching will try to get in all the transformers, but the semantic matching will try to understand in what context he is talking about. Am I speaking about the movie Transformers? Am I speaking about the paper, the transformer algorithms, all those stuff? So that is semantic matching. All right, so here I think Chip has mentioned 3-4 algorithms. It was actually pretty condensed for me. I think 2-3 pages, 6-7 algorithms. So I try to like dig a little bit deep and then see, okay, what's happening there. So if there is anyone who understands this graph algorithms or vector algorithms, feel free to jump in. I've tried to like learn all this stuff from Pinecone. So I think you might have heard of Pinecone. It's a vector database. So they have a beautiful blog. I think that all these vector database guys have beautiful blogs. So V8 is one guys. They have like beautiful learning blogs, and then Pinecone is also doing justice to that. So whatever I have understood here is from a Pinecone blog. So the first one is term-based retrieval. So as I mentioned, this is just looking at the words, right? I mean, just checking if I have that exact words in my vector data bank. So I have 3 contexts. So the quick brown fox jumps, a lazy dog sleeps, and then the third one is the brown fox and the lazy dog. So what it does is that it tries to see, I mean, in each of the documents, it tries to count the exact number of words or the occurrences. So in the first one, you see that, I mean, quick is mentioned 1 time, brown is 1 time, fox is 1 time, jumps is 1 time. The rest of the things are mostly zeros. The same thing for document 2 and document 3. So what we can see here clearly is that on the first site itself, it's just a matrix of ones and zeros. So that is for me sparse embeddings, right? So there is no lot of information. Everything is really sparse. It's just ones and zeros, nothing else. But then the fun doesn't end there. So we go into the step 2, and then what we do is that we calculate something called as term frequencies. So that is something like number of times T appears in a document. A term appears in a document by total number of terms in a document. So if you can, so that just means that so quick just happen 1 time. So 1 divided by 4, 0.25, something like that. So that is your term frequency. And then the next one is the IDF also, the incidence. So here, what happens is that so you multiply. So the algorithm TF IDF, what it does is that it multiplies your term frequency with a log of n by df. So that means if you have a it just want to like penalize the documents, right? So if you have a lengthy document, then it's a given that so a particular term can occur multiple times. So in order to penalize that, then you're taking the logarithm. But then again, you can see here that it's again a matrix of zeros, and then so most of the values are zeros, and then you have some symbol other scalar values like 0.058 here. So it's all in scalar embeddings. So this is how it finds out. So this term-based retrieval, so it's also used in Elasticsearch, but here it uses something called as inverted index. So inverted index is a dictionary that maps from terms to documents. So again, what we have seen here, TF-IDF. So Elasticsearch builds on the TF-IDF, but then it adds something called as inverted index. So it's a dictionary as we see in the table here. So, so you have some terms called banana. So it's found in 2 documents, and then along with this document count, you have some tuples or some dictionaries here that have information like document count and term frequency. So the banana is also found in document 10 3 times. It's also found in it's all found in document 5 2 times, etc. So again, this is how you use, basis of an Elasticsearch algorithm. So then, just a sec. So so now we are building, right? So what is TF-IDF using or doing? Then so the Elasticsearch, the final one is BM25, the 25th version of BM. So what it does is that what BM25 does is that it normalizes term frequencies caused by document length. So I told you before, right? So if a document is really big, then it means that, okay, some of the words can also occur multiple times in a document. So we just need to like penalize that so that our model finds the right document in a faster way. So that's what we are doing in BM25. So we are penalizing the term frequency score. So this is what I found out the major difference between TF-IDF and BM25. So everything is incremental. So BM25 is the latest algorithm that's used in Elasticsearch now, and TF-IDF was the legacy version. And then the term frequency scaling in TF-IDF, it was linear. So if you have a longer document, then your TF-IDF value will be higher in that way. And then, as I mentioned here in BM25, you are already normalizing that. All right, so that's about the sparse retrieval. So everything, as I mentioned, for the term-based retrieval, so everything was just counting the number of terms or the occurrences of a particular word in a document. So the information was gathered based on that. So now we land into embedding-based retrieval. So here, this is the basic difference that I found out. So term-based retrieval, it just counts the relevance at a lexical level, so vocabulary, right? So if you have a vocabulary called dog, it just counts the number of occurrences of that word dog, and then it doesn't consider the semantic information there. And embedding-based retrievers, it see how much, how each and every word aligns with the query, like how to get the context out of the query. So that's the embedding-based retrievers. So so here embedding-based retrieval. So again, there's the same thing. It's a classical thing that what we are using in the RAG nowadays. So I'm taking the same diagram again. So it has this embedding model. So it converts the query into an embedding using the same embedding model with which I already converted my documents. And then the second step is a retrieval. Depending on the parameters, it fetches the related k chunks. So k can be 5, k can be 10, depending on the parameter that you give. And then so it matches like which embeddings are closer to my query. It goes to my vector data bank and then gets all my 5 relevant embeddings. So that's the retrieval part. So this is the embedding based retrieval, is the retrieval what we are, or is the RAG tech what we are using nowadays. I mean, term-based retrieval, I haven't seen honestly, because we want to like focus more on the semantic part rather than lexical part of the things. All right. So the important thing here is the vector databases, right? So because everything is stored as numbers here, we are not storing the information in the term base, right? There we have seen that, okay, we are storing the information as some kind of an inverted matrices, TB-IDF, all those algorithms. But here we are storing the information based on vector database. So it's everything are vectors. So as I mentioned before, both the content and the application, I mean, all the context for your application, everything is embedded in a model. I mean, using the embedded model, it creates the vector embeddings, and those vector embeddings are then sent to a vector database, and then the informations are stored here. And then if you want to get something out, you query the result back to the applications, and then the user get the information. So in the vector database, the easiest part is storing, but the difficult part is vector search. I mean, you create some vector embeddings, and then now with all these LangChain or all those stuff, I think it's really easy to like create a vector database, and all the interfaces from Chroma, VV8, Pinecone, the famous databases out there are really easy. So it's the easiest part is the storing, but then the difficult part is the vector search. We want to get the exact context for the model. All right, so there are lot of algorithms to get the information out of a vector database, but the core idea is a vector search. So here you can see that. So if you have a vector database like here, so there's a vector database of songs. So I query that, okay, I need to hear some thrash rock. I don't know who of you guys are a fan of rock here. So if I ask something like that, so in here you see a vector database, and then I can see that, okay, my query is here on the green point, and then I'll try to get the nearest neighbors to that. So depending upon the number, so if I say I need to get like 5 nearest neighbors, then I'll get in, I don't know, Anthrax, Metallica, Slayer, and then Van Halen. Ideally, it's not thrash, so I just get 3. And then I'll get the information out of that. So it's all based on the ranking the vectors based on the similarity scores, and then I tell that, okay, if my query is landing in between, then I'll get 5 or 10 nearest neighbors. So that's how the thing works. And the most commonly used metric is the cosine similarity. There is a lot of similarities, right? So one of the easiest and intuitive is the cosine similarity. So it checks 2 vectors and then see which one is closer to each other, and then gets the information for my model. All right. So next is LSH, or local sensitive hashing. So again, everything goes to Pinecone here for the beautiful block. So here, the thing is that, so the idea, as we mentioned in the previous slide, is cosine similarity. But then if you have a vector data bank with, I don't know, millions of vectors, so it's pretty difficult to like go through each and every vector and then calculate the cosine similarity and then get the results, right? So it's impossible, or it's possible, but then takes a lot of time and cost. So that's where we are now heading in, how to optimize this vector search. So one of the algorithm is LSH, locality sensitive hashing. So what it does is that it has an hashing function, and then whenever it sees similar vectors, it tries to hash all those vectors and put in similar buckets. So if I come back to the previous example, like if I want something like thrash metal, so what I'm searching in locality sensitive hashing is not going to the complete Spotify music list. Rather, I'll go to a hash bucket for thrash metal. And then, so here it's it's straightforward in duty for me that, okay, I'm just going to that bucket where I believe all the thrash metals are embedded, and I can get the relevant information out of that. So the key idea here is that if all the similar vectors are hashed and then kept in the same buckets, and then it speeds up the process, the search process. So the next one is navigable small world. So there is NSW, navigable small world, and then there is hierarchical NSW. So again, the key is the same. It always tries to get the nearest neighbors. So here, if you see that, so this is the entry point of my query, and then it just goes into it just does a greedy routing search. So it goes from vertex to vertex and then sees that, okay, where will I find a place or a local minimum where there is no other vertices near to my current vertex. So it just goes through that, goes through each of these vertexes and then see, okay, I land somewhere here, and then there is nothing else close to my query vector, so I'll get all those vectors with me. So there's NSW, and then there is something called a hierarchical NSW. Here, the only difference is that they have the vectors are aligned in some different layers, and then again, the cool thing here is that, I mean, it just finishes one layer. It sees, okay, I'm landed here, and then if I don't find the related vectors in this particular layer, then I can go to the next layer. I can find information. If the information is not there, then I can go to the next layer, etc. So again, the complete vector database is connected into layers here. So that's the difference. The other one is product quantization. So here, again, the easiest thing or the intuitive thing to understand is that I have a big vector. What I'm going to do is that I'm going to decompose this vector into multiple small sub vectors. So you can see here that if an original vector is something of 128 size, so it's an 128 to 32 bits, so it's like around 512 bytes of information. So if I divide this vector into 16 small equidistant vectors, and then you quantize everything, so end of the day you land in 8 bytes. So the thing is that you try to reduce the dimensions of your big vector into small dimensions. So it's basically a dimension reduction algorithm. And then so then if you have like small vectors, it's easier to work with. So to compute all this cosine similarity or any other similarity algorithms, it's much easier to work with a small vectors. So that's what's happening here in the product quantization algorithm. So the next one is something called as inverted file index. Again, 8 clusters. So you see here, right? So I have like 3 different colors. That means that each of the vectors are classified into 3 different clusters. So if you have a query vector that lands in one color, for example, the magenta color here, then I can tell that, okay, all the vectors that are in, if I land in this particular quadrant, I can say that, okay, I don't need other vectors from the other quadrants. I just need the vectors from this quadrant for my algorithm to process. So that's what's happening here. I mean, the thing is that if the query lands in somewhere in the border, then there's an issue. So then the intuitive way is that you don't divide this big chunk of vector embeddings into 3 quadrant. Rather, you try to divide into, I don't know, 5 or 6 quadrant. Then the issue with the edge will also be solved. So there's an extra parameter for that. All right, so that was the major algorithms that were seen. I know I just skimmed through the layer. I didn't go through the minute details, and I didn't program all those things also, and show you the code also. But then it was really interesting to see how each of these things work. Because I mean, when we work with RAG, I think what we just do is like you pass the algorithm without knowing what's doing under the hood, but it does the job. But then other way around, I mean, it's also better to get some intuition like how the things is working on a higher level. So that's what I've done here. So comparing retrieval algorithms. So there are, like, as I mentioned, two algorithms, right? One is term-based retrieval, and the final one, or the other one is the embedding-based retrieval. So these are the multiple features that I've tried to compare. So one is, of course, the speed. In term-based retrieval, it is faster because everything is sparse, right? I mean, the vectors are just mostly the zeros, and then there are some non-zero values. So the indexing and query will be, of course, faster. The computation cost for the term-based retrieval is also lower, because in the embedding-based algorithm, you have to convert everything into embeddings, and then that can be really expensive. I think most of the embedding models from OpenAI or the other models, those are really expensive. I mean, it even stuck us because, I mean, when we try to create an RAG pipeline, you start with some embeddings, so 3,000, 4,000 documents, and then you see that, okay, you have missed something, you have to tune some hyperparameters. But the worst thing with embedding-based retrieval is that you have to recreate your vector data bank again. So I don't know, if you want to create a vector data bank, it might cost you $1,000. But then if you want to tune that and better that, then you have to spend that $1,000 again. So computational cost of an embedding-based retrieval is really expensive. There are some cheaper models out there, but then still, yeah, I think you got the point. Then the other factor, like, yeah, ease of use, out of the box. I think term-based retrievals are mature solutions because it's now, I mean, Google is using that BM25 and all those models, so it's high, it's mature. Embedding, it's moderate. As I mentioned, if you create a vector database and then if you want to fine tune it, then we need to, like, see which models are good. You have to compare the outputs of different models, all those stuff. So it's not that easy. If you get a tip from the other fellow RAG developer, then it's easy. Then you can just stick with that model and then do the embeddings. Performance or improvement potential in a term-based retrieval, it's limited because it doesn't have that much tweakable components. In terms of an embedding-based retrieval, you can fine-tune it, but then again, each and every fine-tune will burn a hole in your pocket. So that's one thing. Keyword handling, it's explicit here in term-based retrieval. So what with keywords, it's something like an error diagnostic codes, right? So I don't know, ISO triple one, triple two, something like that. So those words will have a meaning, exact meaning as a term, but if you convert that into a vector, the meaning of that will be completely lost. So in terms of keyword handling, so if you are working with some kind of documents with a lot of keywords for the error, debugging codes, etc., then you need to find something called as hybrid solution wherein you mix the term retrieval and embedding, because in embedding it's really bad. I mean, the keywords will be zeros and ones in embeddings, and no one will understand what is that. So the same thing with the specific terms here. And finally, to the example, so term-based retrieval, as I mentioned, BM25, Elasticsearch, those stuff, and then embedding-based, it's FICE-based retrieval. I mean, the Facebook's algorithm and the sentence transformers. So these are the examples of those algorithms. So then I touched on this point, right? So I strongly believe that the complete strength of the RAG pipeline is on retriever. So if the retrievers are bad, then your RAG pipeline is bound to fail. So how can we improve the quality of the retriever? So there is, like, mostly two metric. So one is context precision and the other one is context recall. So the precision is like, for a query that I'm gonna ask, what percentage of, and I got some documents from the retriever. So what percentage of those documents are relevant to the query? I don't need so if I'm asking about transformer, I don't need any documents related to, I don't know, XGBoost or something like that. So that's my context precision. In context recall is that out of all the documents that are relevant, what percentage is important for my particular query. So in order to do that, there is something called as Ragas. It's an open source tool. So that's also what we did in our project. So we use Ragas, and then all this context precision and context recall was straight out of the box. You have to like, of course, give the context information in your training data set in your data set. Once you can do that, then the ragas can give you straight out of the box answer. So then we can see that, okay, there is something wrong, right? So if I'm seeing that my context precision and context recall values are less, then I can see that, okay, in my RAG pipeline, I need to work a little bit on the retrieval side. And if I see that, okay, there are some other metrics like faithfulness and answer relevancy for the generation. So if those metrics are varying, or if those metrics are failing, then I can see that, okay, I need to work on the generation part. That is a bit difficult, but then that's what, I mean, I think most of the experts work in this part, on the retrieval part, to improve the RAG pipeline. So in order to optimize, there are 4 steps. So all these things comes under advanced RAG, right? So that's what I also touched in the previous is RAG dead or alive slide, right? So RAG starts with basic RAG. We just try to set a retriever, set an embedding model, a vector database, and then it will work, right? For 1 or 2 document, it will work. It's pretty easy to set it up and work. But then as soon as you have like, I don't know, thousands of documents coming in, a lot of issues with your pipelines, all those stuff, then it gets messier. Then we need to like optimize. So then the next stage is your advanced RAG. So all these things, so trying out different chunking strategies, trying out or adding a re-ranking module, using inquiry rewriting, all these things comes under advanced RAG thing. So that's what we are gonna quickly go through. So I've tried to put in everything in as a table. So chunking is basically, I have a big document. I want to like I want to convert those big document into small chunks. And then I have to put that into my vector database. So that's my chunking. So you can do that in a multiple way. You can tell that, okay, I'm using a fixed size. That means 100 tokens or 100 words. I go through my document, take the first 100 words, convert that into vector database, convert that into embeddings, and then save that to vector database. That's my fixed size. Then I can do recursive. That means I split my documents hierarchically, like sections, paragraphs, subsections, all those stuff. I can try to be semantic or content aware. So that means that if I have a code block, I don't want to cut in between, right? So if I'm inside a for loop, if I want to convert a Python code into an embedding, I don't want to cut, inside the for loop. So I want to like maybe get the complete Python code and then into an embedding. So that's the semantic embedding. Token based is that if I have a model with a token size of 64K, then I can convert that convert the document into chunks based on 64K tokens. There's something called as overlapping. So that means you don't take the words individually. Rather, you try to add some overlap in between the words to give it a bit more information. So all these are the different chunking strategy, but then now with LangChain, it's pretty easy. So it's a platform where you can build everything, right? So all the agents and RAG. So what we do is generally there is it's a parameter. So you start with, I don't know, fixed size, and then you get to try you run your RAG pipeline. If you see that you are not getting the results, then you do the other chunking strategy, recursive, and so on. So that's a small table where I try to compare different chunking strategies. The next one is chunk size. So chunk sizes can be like 100, 200. Again, it's a parameterizable value. But then, yeah, I mean, if you have a smaller chunk size, you have higher information diversity in comparison with a larger chunk size. It fits inside the model well. If you have a big chunk size, then it won't fit inside the model context, etc. So these are the other retrieval optimization you can try out. So if your model is not working well, if your RAG model is not working well, what you do is like you check your chunking strategy, you go through all these things, you try to improve. If that is not working, then you go into chunk size and then to tune that parameter. The other one is re-ranking. So re-ranking, the thing is that you tell your model that you tell your rack that, okay, I'm going to take five documents or 5 chunks based on that parameter k equal to 5. But then it can be, and then you give that 5 documents into your model context. But then the information can be in 6, or information can be on 7th document. So what retangling does is that it gets all the relevant documents from the vector database, and then using a better model, it re-ranks those documents. So that there are some large language models that prefer to have the information on the top. So for those models, if you have a retangler that changes the priority of the documents, then your final RAG quality will be really high. So the other one is query rewriting. So if you have a query like, when was the last time John Doe bought something from us? The AI knows the answer. But then if the user just asks, how about Emily Doe as a following question, it doesn't know, because it don't have the exact context, right? So what query rewriting does is that it rewrites the query from the user into when was the last time Emily Doe bought something from us. So here the context, like it bought something from this shop, this information is already given to the model's context, and then it can give the information. So that's an intuitive way of improving the model. The final one is contextual retrieval. So it was introduced by Anthropic in cloud. So what it does is that it augments each chunk with relevant context. So whenever you take the embedded chunks, what it does is that it adds some context to all those chunks. So for example, if it is an e-commerce product, then you can add a description of that product and the number of reviews. So if it is a 5-star product or a 3-star product, if it is an image or videos, then you can add the title and captions of those videos or images. If it is a customer support, then you can add some relevant or related questions. So how the question was solved in the last time, something like that. You can add those information. So that's a contextual retrieval pipeline done by Anthropic. So whatever we have seen till now, so I mean, I think I've touched upon all the algorithms of the retrieval. Any questions, guys? Or I can go ahead.
Is that everything, Vishnu?
No.
Oh, okay.
Okay. All right. So then I'm going into the multi-model track. So whatever we have seen till now is in everything related to text, right? So your the documents are text, you are getting the answers as text. But then the multi-model track, what it means is that you can even embed the images. So if you have images of I don't know, some animals or something in your book or your document, what you can do is like you can create the image description of that particular image, and then convert that into embeddings and then store that in vector database. And when the user is asking something about that particular animal, in our case, then what the model can provide is actually the image itself. So that's actually a cool thing. So you're not getting a description from the embedding, but then rather you're getting the exact image of the image as an output also. And then the final thing with RAG is tabular data. So if you have an tabular data, like, I don't know, SQL database, or you have some structured data, and whatever we have seen till now with RAG was that it was handling the unstructured data very well. I mean, a lot of documents, a lot of images, a lot of text files, etc. But then here, what we see is that it can also work with the tabular data. So what it does is that it has this information, these tools like text to SQL, and then SQL execution. So if the user has something like how many units of fruity were sold in the last 7 days, it converts the text into a SQL code, and then it executes the code. And then once the answer is done, it passes that to the generative model. So there is RAG with tabular data, but then I guess, yeah, there is a form of an agent, what you're going to see in the next slides. All right, so that was it about the RAG. I think in this book also the information regarding the RAG was really good. There's a lot of information. Agents was little less. So I think I can fly through the agents in the next 10 minutes, I guess. So what are agents? So I think that's the biggest thing right now, the hot topic right now. Everything else is outdated. I mean, when you see or open LinkedIn, everyone are working with agents, all those stuff, right? So what is an agent? So it's a beautiful blog. Even I have added this as a reference. So it's from Martin. So yes, I wrote this book called as Hands-on Large Language Models. So he's really famous for all his whole visualization. So I have took the liberty to use some of his visualization here. So what is an agent? So agent, it's an combination of an environment it operates in plus set of actions it can perform. So here you can see that the agent has some sensors. That means it can analyze which environment it's in. So if it is a coding agent, so it understands that, okay, I'm in a coding environment, I'm inside Python, stuff like that. Then it has something like an effectors that can convert whatever it perceives to the actions. So the actuators are basically your tools that the agent can work with. So that's an actually a very good overview about an agent. So what is a difference between an agent, AI assistant, and a bot? So I don't want to like spend a lot of time, but then actually there's a question that I get a lot of the time. Okay, this is the same thing what an assistant is doing. So what is now cool with all these agents, all this hype, right? So the important thing is that the agent can autonomously and proactively perform tasks. You don't need to continuously chat with the large language model. Rather, it can do the work for you. So if you can ask, so take for an example, if you want to write a blog, so what you do is that you go to ChatGPT, you tell to write some text for your blog. So you got your result, then you ask it to correct for grammar. You ask it to make it concise, something like that. So you continuously chat with the model, or you continuously tweak the response what you got from ChatGPT. So in case of an agent, what you do is like the agent has access to many tools. So let's say you built an agent with Grammarly as one of the tool. You have a large language model. So when you tell that, okay, I need a blog, so in the first step, it generates the output, and then in the second step, it automatically passes that output to Grammarly and then correct the grammar and everything. So everything is autonomous here. So that's the big point that one needs to take, one needs to think about when you compare an agent versus an assistant. And then everything, it is goal oriented. So if you tell that, okay, I need a blog with concise information and all those stuff. So that's the goal that you give to an agent. So the agent won't stop unless that goal is achieved. So, but then we need better models for an agent because there are like multiple steps that an agent performs. So if you have an error in first step itself, then that error propagates through the following steps, right? So I don't know if you want to say it like numerically. So if I have a 10% error in the first step, then that error can compound, and then finally you'll get an answer from your agent that might have 90% error, something like that. And then agent, as I mentioned before, it's of higher stakes. We need to do the stuff in an autonomous way. So therefore, we also need better models. So the important thing with agents are the concept called tools. So it helps an agent to perceive the environment and act. So there are two types of tools. One's for knowledge augmentation, and one is for capability extension. Knowledge augmentation, simple examples, something like an image retrievers, SQL executors, email readers, etc. So it gets the knowledge from somewhere and then gives the knowledge to the model. The second is capability extension, something like time zone converters, something called as calendars, math calculators. So if the model doesn't need to calculate stuff on its own, it just calls this tool, it extends its capability, and then the final answers, it passes the final answers to the user. The other important aspect is of planning. So once you send an query to the user, or sorry, send an query to the agent, it goes into the planner mode, and then it's also really important because it decomposes the possible ways in which it can solve the issue, and then it finds out the best way in which it can lead to a successful outcome. So that's what the planning is important for. Otherwise, it will just do a brute search, and then you'll not be satisfied with the answer that you get, and it will be really costly also. So that's what the planning is important for. And then for the plan generation, the simplest way is prompt engineering. So here you see that propose a plan to solve the task. You have access to 5 actions. So I have access to 5 tools. I, in the sense, the agent. And then inside the prompt, so you give an example like, tell me about Fruity Fedora. And then the plan is that if you get the questions like this, then you need to like use these particular tools to generate the responses. So if you're telling the agent that, hey, I have these examples, so you're prompting the agent in a very simple way, and then the next time when the agent gets that similar kind of questions, then it can follow this particular plan. So that's the simplest way of plan generation. Otherwise, the other approaches are, the one is like write better system prompt with more examples. So you can tell that, okay, if you need to like do this stuff, so always go to tool 1 to tool 3, and then you give that order, and the agent will perform that in a similar way. And then you need to give a better description of the tools and parameters. So then the model will know that, okay, I have access to these tools, and for these tools to work, I need to pass in these parameters. So the description should be correct. You should not pass very complicated tools. Rather, you want to like make your functions or the tools very, very similar so that the models can understand. And always use a stronger model. I think Cloud 3.5 Sonnet and 3.7 Sonnet. The difference was that for an agentic application, Cloud or Anthropic was telling that always use 3.7. And then for plan generation, you can also fine tune the models. But I guess even if you keep in mind these first 4 steps, I think we are in a good place. So the next is function calling. The next part. So how will an agent call the functions? Right. So here's a function, or here's 2 tools or functions to convert pounds to kilogram, and then function to convert feet to meters. So if I get a user query like I need to like convert some I don't know 100 feet to meters, then we have to have a proper tool description. So here you can see that, okay, for this tool, it's the name of the tool and the description of what it is doing, and then the parameters. So what all things it needs to give the output. So planning control flow. It's like sequential, parallel, based on some conditions. So if, and then some for loop, that means it just continues that particular task, right? So let's go to 1. So for example, if it is in sequential planning, that means that if I want to talk with your data, so I'll translate my query into some SQL test, and then the next task B is like I want to like execute that SQL query, what I already translated from the task from the previous step. So it's a sequential process. So there are different control flows. So as I mentioned, just because of time, I think I'm only going through the first one. So there is two important concept here. One is react, and then the other is reflection. Everything is again planning, right? So what is react? React is something called as reasoning, reasoning and action. So at each step, so here, for example, I have asked a user query, what is the current price of a MacBook Pro in US dollars? So the model always thinks in two steps. One is reason, so that's the thought process, and the second is action. So first one is it thinks that, okay, I should search the web for current prices. The action is web, domain, so Google, and then the current query is price of MacBook Pro. And then, so it got the answer. And then the model output is like the observation. A Google search showed that the price of MacBook Pro is an average $1,300. So there's the cycle here. So it always thinks like what to do before, and then it performs the action. The second one is reflection. Reflection is you always ask the agent to give what it is thinking actually. So here you have given a task. So there is a list with two words with parentheses, right? So in the first trajectory, it calculates, okay, it writes some program. But then since we are in the reflection, the agent self reflects and tell that, okay, whatever I done is wrong, because it just counts the total number of parentheses, but it can make a mistake when there are multiple parentheses, stuff like that. So there is a reflection, and then the agent can automatically correct that based on the reflection, and then it goes into the next trajectory. What are the agent failure modes and evaluation? So simple, straightforward planning failure. So if you have an agent built in, if you have used an invalid tool, right? So if you want to like convert pounds to kilograms, and if your tool is doing pounds to meters, then your agent will give an answer. It doesn't wrong answer. It doesn't mean that the agent is wrong. It's because your tool is invalid. And the invalid parameters, for example, if you pass in instead of lips, if you passed in kilogram, so that's also wrong. So that's again a chance for a failure. Invalid parameter values. So instead of 50, if the model understood as 500, and then of course you'll get a wrong answer. But then again, the issue is not with the tool, rather than the issue is with an invalid parameter value. The way in which you passed the value to the tool was wrong. So how to check all these things? So Chip has given a very beautiful idea. So it's a planning data set. So you have to have a data set for an agent. And then once you create a data set for an agent, then you can test your agent based on that particular data set. Like how many valid plans that particular agent was calling. How out of total plans generated, how many of those total plans were valid, how many of the tool calls were valid, etc. So it's an actually a pretty good write-up by Chip to check the working of an agent. Again, tool failures. I think I'll skip here. The final concept is it's of an memory. So there is three types of memory for an agent. So one is internal knowledge. That's the information that an LLM model already has. But on a broad way, there are two types of memory. One is short-term memory, and one is a long-term memory. So if you chat with an agent, if you ask me, hey, what's my name? It doesn't know. Then you can write, my name is Vishnu. But then if you ask it again, it won't understand that, right? Because it doesn't have the memory. But if you are inside the chat, inside that particular session, it will know that you are Vishnu. So there is exactly what a short-term memory is. You are inside that context, you are inside the session. But then there can be a use cases wherein you need to like extend this memory, because I don't know if I don't want to like tell that I'm always Vishnu again and again to my model, right? So then you can have some databases and you can store that information so that that's persisted with my agent. So that's something called as long-term memory uh, or an external, external data. Yeah, I think it's already 15 past. So I think we can have a wind up. It's the issue is that there's tons of information in this particular chapter, and I think uh, yeah, it's very difficult to like finish it in one hour. I hope you guys have understood most of the stuff. I know in some of the places I skipped or I went a bit quick, but then I'll share the slides with you guys. You can have an go through all these slides. I've even linked all the information, the references here, and then we'll get. I don't want to like take it till 17:30 because there won't be any time for the discussion. So let's have a discussion. Last 15 minutes of discussion. Sorry for extending this match 15 minutes, but then hope it's fine.
Not at all. You were completely fine. This was a really good chapter. One that's
Yeah, but a lot of information.
relevant and it started to touch into Anthropic's model context protocols. If any of you have started to use that to build agentic workflows and so on.
Yeah, I like the agentic stuff, the agent-oriented stuff, and she quoted from a book. Let me see if I can find it. She quoted it, which is just a general book. It's Artificial Intelligence: A Modern Approach by Stuart Russell and Peter Norvig, and that's more of a general book. But the two people that wrote the book are very definitely in AI. They're very well known, and it's quite a good book. But it's more of a general non-programmer book, and yet it stresses agents, and I can see even when you're talking to large API LLMs that really you're probably talking to a layer that is agentic because it's safer for them. And it's like I've heard recently agent models described as the hands and the feet of AI. In other words, it makes it real. Rather than expose the LLM to direct access, both the user that wants to use it plus the LLM providing the service have layers of agentic workflows between them.
Exactly, 100%. And then just the one we sort of touched on the evaluations of the output of some of those activities, and the next chapter gets into even fine tuning the LLMs, which are also for when you're attaching to your agents very custom and specific data, your organization's content, your own materials, your own content, and so on. So the LLM doesn't just give something general back, but fine-tuned, personalized, specific content back, 100%. And that's, I think I shared on our Discord the DeepSeek equivalent to which is very similar to the agentic world. This company called Manus, MANUS, their website is manus.im, and they have a massive growing library of use cases which you can replay. Now, again, if you get access and you start running those things on your own, it takes 4 to 6 hours for a full workflow to run. So don't get the idea that the replays are it happens that fast. It doesn't. But still, this stuff is really this is where the rubber hits the road. These are things that large enterprises, small companies are beginning to do, and small companies have to do in order to change and transform their core business models, they can, thrive.
True.
Yeah, go ahead, Vishnu.
No, I mean, absolutely, I agree. And then especially regarding the industries, right? So there was one interesting talk in Y Combinator, and then it was they were telling that okay, for each and every 1 billion revenue companies, right? So there will be an parallel agentic company worth the same revenue. So I find it really interesting and challenging also. So so if you're a startup, I don't think we need to like find some crazy ideas. We can take some company and then try to make up an agentic counterpart of that company, and then you'll still earn. So that's the idea that they were trying to put forward. So I find it really interesting. I mean, where this agentic part is going on, right? So there's one more example wherein people were telling that now there is no need of applications in phone, or rather you can tell that in your mobile phone you don't need any more apps. I mean, you can have an empty mobile phone without any applications, and the beauty is that you only have a simple chat interface. You type what you need and then it gets all the information, so you don't need to have like 300-400 applications installed on your mobile phone. I find that also a really interesting use case for an agentic AI.
So I'm going to make a very snide comment at that. I've heard exactly that same point, and I see it presented over and over at
Yeah,
AI
Spy
conferences.
Telecom, I guess. Yeah.
Yeah, right. And I hear it, and you're speaking the truth. But here's the thing: that perspective will only come from an engineer, and absolutely not a product manager or business owner. Because has anybody heard the word efficiency? So real-time execution of every code does not make a product. And you're going to be all that does is you're going to sell a lot of hardware with rapid compute. Great, we all need it, but there's never any consistency. There's never any standardization. There is never organization. And who's going to pay even $1 for that? So you have a lot of startups who are pitching these sorts of real-time compute and just new models and so on, but they're still stuck in startup phase. The companies that are growing, one that I've been two I work with. One is a very large enterprise, ServiceNow. ServiceNow it has announced in the last 2 weeks their intent to acquire an agentic AI it was a startup because they had only been doing the agentic AI workflow for about 18 months, a year and a half. ServiceNow is acquiring them for $3.85 billion. So a year and a half's worth of focus on agentic AI, and you now get 3.85 billion. Take a look at what the four co-founders are doing right now, even before the deal closes, right? You've got to focus on, and they are all about enterprise frameworks, building on existing stacks, connecting to core systems of record, fine-tuning the models so you are getting something very, very specific, standardization, repeatability, not every run is unique, and so on. That's when you can infuse those solutions into workflows and start to actually enable real world automation.
Yeah.
I'll get off my soapbox now. What do you all think? What is everyone else's experience? Well, if that's all we have, if you'll allow me to take the screen. So thank you, Vishnu. Vishnu, that was an amazing presentation. Really appreciate you for taking the time to prepare and share content with us. So next up is a chapter that is also very, very essential, fine tuning. Is there anyone here who would be able to take a stab at that? It's not quite as involved as this past chapter that we just did with RAG and agents, but fine tuning is certainly an important one. Any takers?
I'm happy to do it if you need somebody.
All right. Patrick has presented once before, did a great job there. Team, anyone else? Otherwise, Patrick's the brave one.
You tend to study really hard when you have to present, so it's a great way to learn.
Indeed.
Yeah, true.
The best way to learn something beyond studying in depth, going to a really good program and so on, the best way to learn something is to teach it.
Mm-hmm.
Truly.
Exactly.
All right, Patrick, I think you are on for fine tuning.
Great. Okay.
All right. Please let me know if I can help with anything. You know where to find me. And with that, once again, I want to wish everybody a very wonderful Eid if you celebrate, and even if not, have a fantastic Sunday.
Later.
Yeah.
Thank you.
Yeah.
You
Bye-bye.
both. Bye.